So we need to take a quick side trip into physics and look at light and electromagnetic radiation. Because how light interacts with atoms was very important in the development of our understanding of how the atom is structured. What is light? Light is electromagnetic radiation. It has an electric field and a magnetic field. It's a type of energy that travels through space at a constant rate. And we very creatively call that the speed of light, right? The velocity at which light travels, the speed of light. In miles per second, it's 186,000 miles per second. It's not miles per hour, that's miles in 1 second. It's crazy fast. I used to watch cartoons. Some of those old cartoons, it's really funny. The old prospector, he blows out the candle, and then he runs across the room and he jumps in bed before the light goes out. That's not going to happen, right? Because light travels across a room almost instantaneously. And yet when we look at huge distances in space, we recognize that a star can do whatever stars do. I'm not an astronomer. But stars self-destruct, and there's some fancy name for that, and I'm not even going to go there. A star can die and its light go out, but we can see the light that was already leaving that star before it died for years sometimes. So light does travel at a finite speed, but it is really, really fast. But it's important to get firm in your head, all light travels at the same speed. All electromagnetic radiation travels at the same speed. 3 times 10 to the 8th meters per second in metric units. And an interesting thing about light is it has properties of both waves and particles. And this is where we get into the whole quantum mechanical thing a little bit. And those are some of the ideas that Einstein worked on. Well, we're all familiar with waves on water. Here's a picture, a surface of water, and if we disturb it, say by dropping drops of water into it, we'll see these ripples. They're little waves, and they will travel outward, and they will keep going. Eventually they'll die out, but they will carry outward. Waves carry energy. Now, if you've ever been at the coast and stood in the surf and been hit by a large wave, you know that there's a lot of energy in that wave, right? It'll knock you flat. There's a lot of energy in the waves. So these waves carry energy. Electromagnetic radiation travels in a sine wave. You may recognize this shape from like trigonometry class. So this is a sine function. And the wave has some characteristics. The wavelength is the distance between the peak of one wave to the peak of the next wave. So that's the wavelength. It's the length of a wave. And that's given the symbol lambda, which looks like an upside down Y. It's a Greek letter. For visible light, that wavelength is what determines the color of the light that we're seeing. So the light is traveling in this direction, but it travels in a wave, and so it goes up and down as it moves. It's a little hard to think about sometimes. If we take white light, such as comes from the sun or from an incandescent light bulb, and we pass it through a prism, we see a rainbow. And when you see a rainbow outside when it's been raining or when the sprinklers are on, it's the little tiny droplets of water in the air that are acting as prisms and separating the light. A prism separates the light according to its wavelength, and you see them, the different colors, all spread out. All of these colors were together in the white light. The prism just separates it out. Color is an interesting thing. Matter absorbs light energy, and it can also reflect light energy. And so something that we see as red, like this woman's shirt, something that appears red to us is actually absorbing all the other colors, and it's reflecting the red color light. It's reflecting red light. So something that appears blue is absorbing yellow and green and purple and violet and red and orange, and it's just reflecting the blue light. Another property of waves is their frequency. So here's a wave. I'm not real good at drawing sine waves. And this wave is traveling in this direction at the speed of light. And it has a wavelength. This is its wavelength. And so it's going to have, what the frequency is say you're standing right here. That's not a comb over, that's just a sloppy head. You're standing here and you're counting these crests as they come past. The number of crests you count in 1 second is the frequency. It's also called cycles per second. And hertz is a unit of frequency. Hertz is cycles per second. So if this wave is going, or we could have a wave with a shorter wavelength, there's a shorter wavelength. This purple wave is traveling at the same speed. If we're counting here, are we going to see more crests or fewer crests in the same amount of time? We're going to see more, right? So this purple wave, can you see the color up there? Kind of. So this purple wave has a shorter wavelength, but the frequency is higher. So that's an inverse relationship. If the frequency is high, the wavelength is low. If the frequency is low, the wavelength is high or long. So light acts like a wave. It can also act like a particle. And that's a little hard to get your mind around sometimes. It's like saying, hey, could you give me a piece of milk? How do you give someone a piece of milk, right? It's a liquid. I can give you a glass of it, but I can't give you a piece of milk. It's not solid. Light acts like a particle. And the word for a particle of light is photon. You've probably heard that word before. Where have you heard the word photon? Star Trek, right? Fire the photon torpedoes, right? Well, light is energy. So could you have a photon torpedo? Yeah, I think you could, actually. A photon is a particle of light or a packet of light energy. It's a discrete quantity of light. A little hard to understand. The amount of energy that is carried in that packet is going to depend on the wavelength of the light. A shorter wavelength has more energy. Light waves carry more energy if their crests are closer together. So let's draw these two waves again. The purple one with the short frequency and the green one, I'm sorry, that one had a short wavelength, and the green one with the long wavelength. Now what I'm going to say is not explaining how things actually are. This is just a way of thinking about it that can help you remember these relationships. Which of those waves looks more energetic? The purple one or the green one? The purple one. It looks like it's jumping up and down, right? And the green one looks all slow and lazy. They're both moving at the same speed, but one of them's going up and down very quickly, and one of them is going up and down very slowly. The short wavelength has more energy. The long wavelength has less energy. So there's this relationship between energy and wavelength and frequency. And I think the best way to remember it is to just either mentally or actually physically draw yourself a picture like this. And oh yeah, that one that's going up and down, that's got more energy. That's got the shorter wavelength, and it's going to have the higher frequency. So you can look at the picture and just figure it out instead of trying to blindly memorize something. Any questions about that section?